In the last lecture, we learned about the infinitesimal generator, which arises as a differential quotient of the semigroup. And so that's a way, if you have the semigroup, you can compute the corresponding A. And then for the infinitesimal generator, we basically proved a fundamental theorem which relates the semigroup and the infinitesimal generator. And then we had another result here. Where is this? About that the generator is a closed operator and it has a dense domain. Now, this all then will lead to a wonderful thing which I call the triangle of semigroups. So let me just quickly talk about the triangle of semigroups. I have that right here. So we have basically three things which we worry about all the time. We have the generator A and its domain. We have the semigroup on top, T of T. And then also the resolvent, R lambda A, plays an important role, as we have seen a few times. And now I indicated here lots of arrows between those, which relate one to the other. So the rest of the semigroup chapter of our course is basically to fill in those arrows. And so I give us some symbols here. So between generator and semigroup, we have the sun and the moon. Between semigroup and the resolvent, we have a horse and a cow. Well, I apologize for my terrible pictures. And then for the generator and the resolvent, we have a mouse and a snake. And so I would like to fill in all those symbols with mathematical expressions, explaining the relations of those. So a few of them we know already. So for example, if we have A and then want to compute the resolvent, so then here let's remove the mousey thing. We can write that the resolvent R lambda A is of course A minus lambda I inverse. A minus lambda I inverse. Similar for the snake, if you have the resolvent, you can invert this and find A. So A is the resolvent lambda A inverse plus lambda I. You just revert the equation from above. And now with the generator, we learned something about the sun. We can come from the semigroup to the generator. So A was the limit as, now I write it in T. T goes to 0 from the top. T of T minus identity divided by T. All right. So that's already neat. But we would still like to find something for the moon, for the cow, and for the horse. But before I do this, I come to the solutions of abstract ODEs. And here we come back to the idea of a mild solution. I think we talked about this before. Okay, let's jump right in. So first of all, I talk about a classical solution. Classical solution of what? Well, we have a differential equation right here, with an initial condition giving in a Banach space. And then a classical solution, we define a solution which is in this space here. So which means it is C1 in time and then has values in X, which is the Banach space. And it is also continuous in time, but then it has values in dA. So this basically means that we can differentiate both ways. We can differentiate in time, given by this, and if A is a second derivative, then we can differentiate in space given by that. And this is kind of the funny way to write this down. You might wonder, you might want to write this to be C0, C1 in dA, but this is a much smaller space, so it's a much stronger condition, which we don't really need. We only need this weaker formulation in the pink box. So this is something, well, sometimes it's true, might be true, but for the general theory, it's maybe asking a bit much. If A is the generator and T is a semigroup, then we can write down a variation of constant formula like I do down here. Okay, so then the solution of the equation above, 8.3, is given as TTU0 plus integral from 0 to t, tt minus s f of s ds. Well-known formula and very, very useful. Now the proof is actually rather straightforward. You basically just compute this stuff. A smart way is to introduce a g of s to be t minus t at t minus s times u of s. And then we differentiate g. So if we differentiate g, we have a product rule. We first differentiate the semigroup, which gives us the a on top. And then we differentiate by s, so that's why we get a minus sign. We keep the u, and then we keep the t and we differentiate the u, which gives us a u dot. Then the first term is unchanged. For the second term, now we use a differential equation. Let's go back to 8.3. So u dot is au plus f, so which we sub in right here. Now the semigroup and the operator commute. This is also something we have seen in the fundamental theorem. So then the first two terms cancel, and only the f term remains. And now we integrate this over time. So then we get gt minus g0, which is, if you sub in by the definition of g, g of t is actually u of t. G at 0 is tt times u0. Yeah, and then you have the integral of the right-hand side right there. And that's the variation of constant formula. And this is now a reason to define this to be a mild solution. So here we go. Given the differential equation, u dot is au plus f, where f is L1 from 0t to x, then u is called a mild solution if it satisfies the variation of constant formula, which is just hiding on top there. So let's move it a bit down. So this is called a mild solution. One thing to note is that the mild solution does not need any differentiation. What? Why? Okay, let's go back. Because, right, you just multiply with the semigroup. If you know the semigroup, you just multiply. You don't need to differentiate anything. So that's good. And then also, classical solution satisfies the variation of constant formula. So it is, of course, automatically also a mild solution. However, a mild solution is not necessarily a weak solution, right? There's a big difference. Weak solutions we define through a dual space. A mild solution is basically written as an integral. But mild solutions can be used to find weak solutions. Okay, in the next result, though, we show when a mild solution is actually classical. So classical in the sense of the previous page here on top, where I am in this space. This is what I mean by classical. So C1 with values in X and C0 with values in dA. All right. And to have this, we need one of two conditions. We need either f is in W11 with values in X, or f is in L1 with values in dA. And when I go through the proof, you will actually see how these conditions work together. Somehow one implies the other, and the other one implies the first, and so on, but we need at least one of these conditions. Okay, let's start. By the fundamental theorem, we look at TTU0, so the first term in the variation of constant formula. I go back just one more time. Okay, the first term here is a TTU0 term. And this term is good. That's what I'm arguing here. It is differentiable. And it is in the domain of definition, like we have seen in the fundamental theorem. Differentiable in T means it is in C1 with values in X. And TTU0 sitting in dA means it is continuous with values in dA. So this is a classical part all by itself. So what we really need to worry about is then the second term, the integral term, which I write down again here as V. So V of t is integral from 0 to t, semigroup times f of s ds. And we want to show the two things. Here it is again. V is in C1, values in X. This I call 1. It's also C0 with values in dA, which I call 2. So let's compute this. And I compute the differential quotient, which was basically the definition of A. So there's a V missing, of course. I want to apply this to the V, which I just defined just over there. So I sub in the V, which means the semigroups are shifted in the first term by an H, which happens right here. and the second term is unshifted. And then I split this integral up into different parts. So the first integral I make a little bit longer. I go to t plus h, but then I subtract whatever I added artificially right here from t to t plus h. And then the last term I leave unchanged. The first integral is a v of t plus h by definition, and the last integral is v of t. So then I do the first and the last together, and I call this item 4. And what I remain is this artificially added or subtracted term, which is the integral from t to t plus h, semigroup times f of s ds. And now we would like to take the limit as h goes to 0. So can we do that? Let's see. From the fundamental theorem again, we can do it for this term. We wiggle, which we get here, to converge as h goes to 0, and we divide by 1 over h to f of t. So this was one of the properties we have seen earlier. So that's all good. But how about the limits of 3 and the limits of 4? Well, one thing we can see clearly is if 3 converges, and this is an equality, so then also 4 converges. Vice versa, if 4 converges, then also 3 converges. But still, we need at least one of these guys. Let's look back at the conditions 1 and 2 up here. So let's assume v is in 1. So v is continuously differentiable with values in x. Then 4 converges. And then 3 converges. Cool. On the other hand, if v is in 2, so it is continuous with values in dA, then 3 converges, which then also implies 4 converges. So it looks like a circle argument here. And we need to kind of try to leave this circle argument. And this is what the additional conditions for f are for. So let's look, for example, if f L1 values in dA. Then we have automatically that 3 converges. Let's see. L1 in dA, where are we? So again, here's the f. So now this is in dA. So this corresponds to the case 2. And this corresponds to 3. So there's 3 here. So 3 converges in that condition. If L is in L1, L is in dA, then 3 converges by the definition of V. And then 4 converges. On the other hand, if f is W11 values in x, so then we have weak derivatives in time. And then we simply differentiate the V definition. So then we get v dot equals t times f0 plus the integral of the semigroup times f dot. And since f dot arises here in the integral, we get away with the weak time derivative right here. So everything converges and we are done.